All right, the next example is number 70. We are still trying to figure out the inverse function of what we have as given to be f. We set this equal to y. The first step is to interchange the x and the y. So that is going to look like this. The x becomes y. The x becomes y. The y becomes x. And now we get the y by itself. Cross multiply, right? That's going to be our first step. We get negative 3y minus 4 equals x times the quantity y minus 2. We want all of the terms that contain a y to be on the same side. We want all of the terms that do not have a y on the other side. We notice that both terms on the right-hand side contain that common factor of y. We can factor out that common y. And then divide both sides by that leftover quantity. That's going to get the y by itself. So that gives you the inverse function to be 2x minus 4 over x plus 3. And I think that's good. We're not going to verify that one this time. The last example, the last question that's been posed for this section, gives you a function f and a function g. And you are told that x is greater than or equal to 0 in both cases. Given that information, would you say that f and g are inverses of each other? To figure that out, you could draw a graph of f. The graph of f is a parabola, right? But don't forget that x is only allowed to be greater than 0. So we're going to make sure we start here, and then we just talk about the right side. Consider what the graph of g looks like. Square root function. And then decide if you think these are inverses of each other. Consider a couple of points. How about 0, 0? How about 1, 1? How about 2, 4? Those are all on the graph of f, right? To be on the graph of g, if g truly is the inverse of f, then that would mean that the ordered pair 0, 0, 1, 1, and 4, 2 would be on its inverse. Don't forget, you flip the order of the x and the y values to be the inverse. And if these points correspond to what the function g was defined to be, then we can, with pretty good confidence, say that our functions are inverses of each other. So what do you think? Is 0, 0 on this graph? Yes. Is 1, 1 on this graph? Yes. If you put 1 in for x, what do you get for your answer? Is 4, 2 on this graph? If you put 4 in for x, what do you get for your answer? Square root of 4, that's 2. Whoops. That's what we were supposed to get. So we have pretty decent confidence to say that your functions are inverses of each other. Now, it's a good thing that we were told that x can only be 0 or more, because if I didn't have that restriction on the graph of f, I would have had that left-hand section, and if that were the case, I would not have inverses of each other, because that function f with both halves included is not 1-to-1, and therefore its inverse does not exist. But because I've got the restriction on the domain that x is at least 0, I do have two functions that are inverses of each other. I could further go ahead and say that f of g of x should equal x, as well as g of f of x. That should equal x. And you could verify algebraically. That first set would say you would look at f of the square root of x, because that's what g was. You put that into function f, square root of x squared. Does that equal x? Yes, because we were told that x had to be positive. And on that second order, g of x, g of f of x, where f of x is x squared, put that quantity into g. Does that equal x? Yes, because once again, we were told that x is at least 0. Without that restriction, you would have to say, no, these functions are not inverses of each other. So f and g are inverses of each other. All right, that takes care of sections 4.1 and 4.2. And the next class period we're scheduled to have would be discussing what section 4.3. So far I have given you enough information to get through one class period.